All right. So next topic is stability. Stability is a very important topic in controls. Uh, there is a lot of work. Even right now, people continue working, doing research on stability. It's a for some systems, for nonlinear systems, it's a difficult topic to talk about. It has a lot of mathematics. For linear systems, which is point of interest of feedback control systems or automatic control systems course, it's less complicated. So we are going to discuss them here. We initially learn about the definition of stability. What does it mean to be stable? We have previously also mentioned it without really defining. We have said, well, the system should be stable, but we haven't defined it. So here we, for the first time, actually define what stability means, and then we discuss two different methods to assess stability. Routh-Hurwitz table or Routh-Hurwitz criterion is one method, and then we study root locus, which is a graphical tool to investigate stability. So we have learned different ways to model a system. We have previously learned ordinary differential equations and transfer functions and block diagrams and state space representations. Then we have studied the properties of a system. We studied what the final value theorem says. Basically, how can I predict what happens to a system's response if I wait long enough. Then we studied how does a first order system or a second order system react or behave if I give it certain input. Now we want to study stability, which still is in the domain of analysis. We are analyzing a system. So now I have a model from it. I have one of these four ways of describing the system. Now I want to see and learn more about the behavior of it. So here for defining stability, we initially just talk about the concepts, so physical concepts, and then we use transfer functions and see what stability means if I have transfer function of a system. So the informal definition of stability is that it's a measure of tendency of a system's response to return to zero after being disturbed. So a measure of tendency of systems respond to return to zero after being disturbed. So if I have a system, if I disturb it, meaning that if I with my finger move it a little bit, is it going to go back to where it was or not? This is the informal definition. The stability of a linear system can be represented as the sum of two parts or two pieces, the natural response and then the forced response. As you have studied before, natural response is the response of the nature of your system or the dynamics of your system to that input. The forced response is the effect of the input. So if I change the input, what's going to change is the forced response. The natural response is the response due to initial conditions. The forced response is how the system responds to the input. Okay, now let's talk about stability. Let's have the formal definition of stability. There are two different ways to think about or to define stability formally. There is the definition from initial state or initial condition point of view, and then there is a definition of stability from input-output point of view. And these two different definitions, we're going to see one right now and then in a few minutes the second definition. These are not 100% the same. So yes, it is possible that we have a system that is stable uh, based on one definition, and it's not stable based on the other definition. For linear systems, which is what we discuss here in this course, these two definitions match. So if a system is stable based on what you are seeing right now, which is the stability from input output, from initial state point of view, then it is stable from input output point of view too. Okay, so now what's inside of it? So the formal definition of stability for a linear time invariant system is this: a system is asymptotically stable or simply stable if the response goes to zero for any initial condition. So any initial condition, meaning that from any starting point, the response is going to go to zero. So imagine a bowl, and then you have a ball inside of it, right? So you release a ball inside the bowl. Doesn't matter where you start, it's gonna, at the end, it's gonna go to zero. That's an asymptotically stable system, or simply stable. An unstable system is if there exists an initial condition for which the response eventually goes to infinity. So imagine if there's imagine a ball on top of a hill, and imagine if you uh, give that ball a very small amount of force. What happens? Well, the ball is never gonna go back to the point that it started, right? It's gonna go as time goes to infinity, the response is gonna go to infinity too. That's an unstable system from initial state point of view. The third possibility, or the third definition, is a marginally stable system. A system is marginally stable if the response remains constant and bounded and doesn't go to zero. So imagine a ball that is located on a flat surface. If you poke that ball, it's not going to go back to where it started, but it's also not going to go to infinity. That is a marginally stable system. So from initial state point of view, we divided systems into three possibilities: asymptotic stable or stable, unstable, and marginally stable. Another example is the cone. So if you have a cone on tip of it, on its tip, it is unstable, it falls onto its side. If you have a cone that rests on its side, and it doesn't have any tendency to go back to its original position, so it's marginally stable. But if you have a cone resting on its base, it's stable, because it will go back to its original position if it's tipped slightly. Okay, so that was stability from initial state point of view. So meaning that we had these three different definitions, and they all included something about the initial state. There is a state, there is an initial, so there is a starting point. Now, the second flavor of results or definitions, again, we have stable, unstable, and marginally stable, but now we have them from input-output point of view. So a system is stable if bounded inputs yield bounded outputs. So I don't care anymore about starting point and going back to zero or any of these things. I say, well, let's think about my system as a black box. I don't know what's inside of it. I give it some input, and that input is bounded. The output must be bounded. If that happens, your system is stable. Your system is unstable if there is one input, even one, that if you give that input to your system is gonna create an unbounded output. And the system is marginally stable if this is a little difficult, so let me read it and explain it a little slower. A system is marginally stable from input-output point of view if, for bounded inputs with frequency equal to the natural frequency of the system, the output becomes unbounded, but for other inputs, the output remains bounded. So let's repeat again. A system is marginally stable if for all inputs the output is bounded. So that's very similar to a stable system, except there is one specific input that the system is sensitive to that input. Okay, so that seems to be like instability, right? There is an input, there exists an input which makes the system unbounded. That seems to be instability, but it's not. So the marginally stable system says there is an input that makes the system's output go to infinity, but the uh, the frequency of that input is equal to the natural frequency of the system. So that's what is specific about marginally stable systems. Okay, how do you determine stability of a system? These are just definitions. These are the concept of stability. If I give you a system, how would you determine if it's a stable system? Well, we can look at the poles of the transfer function. If I have the transfer function of the system, I can look at the poles. If all of the poles are located on the left-hand side of the imaginary axis, then the system is stable. If there is even one pole that is on the right-hand side, your system is unstable. The system is marginally stable if and only if the real part of all the poles is non-positive, so it's either negative or it's zero, right? So the system is marginally stable if all the poles are on the left-hand side or on the j omega axis. One or more poles has zero real part, and all poles with zero real parts are simple roots. Okay, so stability means all the poles are on the left. Instability means there exists one pole on the right. Marginal stability means that all of the poles are on the left, but there are poles on the imaginary axis. But those poles that are on the imaginary axis are simple roots. What does simple root mean? It's the opposite of being repeated. So there are no repeated poles. Okay, let's see these examples. Pause the video and write down on a paper based on the definitions of the previous slide, which one of these systems is stable, which one is unstable, and which one is marginally stable. All right, so system 1, there is one pole, and the value of it is s equals to positive 2. That is unstable because you are so the pole is on the right hand side of the imaginary axis. System 2 has one pole, and the amount of it is negative 2. So your system is stable because the only pole it has is on the left-hand side of the j omega axis. System 3 is stable. It has two poles. They both are on the left-hand side. System 4 has 1, 2, 3, 4 poles. These three are on the left-hand side, but this one is on the right-hand side. So the system is unstable. How about this? What are the poles of this system? Well, you can write this as s plus 1 squared plus 1. So the poles are at negative 1 plus minus j. So this system is stable too. Both poles are on the left-hand side.